Okay. Shall we start? How are you folks doing? Is there some exam today? So the number seems to be small today. But it's an important class. I don't know. No exam. Ah, okay. Plain and simple. Okay, so there is something else that is a problem. Just a second, I'm just adjusting the window for viewing all of you and the chat. Okay. 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 Oh, any questions? Any questions? Any questions, folks? Would you have any questions? Yeah. Siddharth, I'm feeling wonderful. How about you? You're going to continue the questions from last time? Okay. Well, in the last class, we were discussing about torque transmission systems, and we just started warmed up with trying to find out what would be the internal force resultant provided the external torques are given. The internal force resultant, we named them as twisting moments. Okay. So whenever you're given a shaft and you're given the external torques acting on the shaft, it is possible for you to take the free body diagram and use the free body diagram in order to draw the twisting moment diagram, TMD. Okay, this is what we did last time. But we also discussed about the sign convention and so on. Okay. Now, having found out twisting moment, okay, the next exercise obviously is to find out the stresses, strains, and so on, right? So in order to start with that, let's just do a simple experiment, find out what happens in reality and see if we can understand the deformation that goes on when torque is applied. Okay. I just forgot that I forgot to instruct you that you should get that tube and all those, but anyway, it doesn't matter. Next class probably we'll do that. This is a simple tube element that I have taken. Okay, so let me just draw it so that it's easier for us to understand. What we'll do is we'll just twist this tube element and find out what kind of deformations occur. Okay. So what we are going to do is we just going to take a tube element. Okay, and apply a torque and find out what happens to this tube element. Okay, and based on what happens to this tube element, we will find out what deformation it goes through. Okay. Of course, I know one thing about it. If I twist, that there will be a twist. The angle of twist. I'm sorry. Where am I? I'll repeat it once more. Once I apply torque, the element or the shaft twists, and due to twist, there is an angle of twist that we find out. Correct? Now, I'm going to deliberately take as a circular cross section. The reason why I take circular cross section is so that circular cross section is axisymmetric. Okay. So it doesn't see a difference between this angle and that angle. Whether I take this point or this point or this point or this point or this point, it doesn't see a difference. Okay. So that's where we will start with. Okay. And then figure out what would be the deformation. Based on the deformation, once I get an idea of deformation, then it's easily possible to look at stresses and so on. Okay. That's how I'm going to proceed. Okay. Just a second. This is disturbing me. All right. Now, let's do the experiment now. Just a second. Yeah. Are you able to see this? Okay, this is the shaft. This is the shaft I have. Okay, and this shaft I'm going to now twist. Okay, are you able to see? I've drawn a grid over here, and lines that are cross-sectional lines, circular lines across the cross section. Okay, so now I'm going to twist. How will you know that I am twisting? This point, sorry, this point and this point will now shift. You can see it now. You're able to see? So I'm just going to hold. Yeah, okay. This is my right hand, this is my left hand. Okay. Are you able to see? There is a shift of these 2 points, this point and this point, right? You can see that shift happening. Right? I'm twisting now. Let's understand what happens here. Can you figure out what happens here? Again, I'm going to do it once more. Just watch it carefully. Are you able to see it? Yeah, are you able to see it now? This is the original. This is the deformed. Okay. What change do you see? What change do you see? Shall I repeat this experiment once more? I don't know why it's okay. This one and this one. So I'm going to now twist it. I'm twisting it now. Okay. What do you find? What happens to the grid? And what happens to those circular lines? Let's start with that.
Grids become parallelograms.
So we had something like this. This was a grid that we saw. And we also saw lines that were drawn, circular lines that were drawn like this. Okay. So those which were almost rectangular in cross section became parallelograms, right? So what really happened was I'll just use it to do something else here. So they became something like this. I'm just exaggerating. What was initially like this now started to become like this, right? So this is one observation that I see. Okay. So from rectangles to parallelogram. Okay. What other observation do you see? This is one observation. What am I trying to do? I'm trying to find out what could be the deformation that this is going through. Okay. Grids rectangle become okay, parallelogram. What else? What else did you notice? What happened to these circles?
So they become ellipses.
Just watch it, watch it. Don't notice my hand because I'm pressing it. That's why. What is happening? Ah, okay, yeah. What's happening?
Spacings between circles decrease.
Decreased? Just notice it carefully. The circles are rotating. Very good. So circles are rotating is correct. Circles are rotating. If I take this line and this line, were they expanding? No. So there is no change in the length of, I mean, the gap between them. All right. They were just rotating as circles as they are. Right. This is the deformation that I'm seeing as far as a thin tube is concerned. Okay. With this assumption, with this understanding, let's see if we can find out what deformation this shaft, which is thin shaft, undergoing torque is undergoing as deformation. Okay. Just to give you a little bit more explanation. See, today I'm just, yeah. Why is it not visible properly? Are you able to see it?
It's blurred, sir.
Yeah. Okay. One side of it is, okay. Are you able to see this side? I'm not able to see this side. Okay. I don't know how to show it. Okay. Let me show it like this. Here also. Are you able to see now?
Yes, sir.
Okay. So this is the initial grid. Okay. After applying the torque, it became like this. Oh, it's tough to get this. Now you're able to see, right?
Yes, sir.
From what was square, now it has become parallelogram like this. Correct? The circles also only rotated. That's all. The lines that were parallel to the axis rotate. I mean, became slanting. Correct? Right? One more experiment so that we are clear about it. So I'm now twisting it. Are you able to see?
Yes, sir.
All right. So what we observe is just that there is a rotation that happens of this circle. So if there is a point over here, that point has shifted over here, right? And they become parallelograms. Now I need to find out what would be the deformation. What kind of deformation is this? What kind of deformation is this? What was initially, so if I take one single square or a rectangle, this has now become parallelogram. What kind of deformation is this? There's something wrong. I'm not able to see this. what kind of deformation is this? What kind of deformation? How come no twisting? What other? When I say deformation, I'm talking about
Angular
strain.
deformation.
Strain. This is symmetric. In a way, it is anti-symmetric. That is, if there is a rotation that is happening, there is an anti-symmetric movement that you see, right? It is called anti-symmetric. The structure is symmetric, but rotation is such that it is anti-symmetric. And what we see is a shear strain, correct? Right? And this angle is going to give me the shear strain. Yes? Yeah. That another thing that I noticed is if I take one point over here, that point which is the same as this point along the same axis, now has shifted and taken over this position like this, right? So there is an angle that it has made. This is angle of twist, right? Right? Supposing I had taken a longer one, applied the same torque, it would have twisted by a different angle, correct? Yeah. All right. Sorry. Somewhere I'm just getting stuck. Okay. Now, I know this is gamma. I know that this is the angle of twist. Are these two same? That's the first question I'm going to ask. Okay. So let me repeat it once more. I have this and it has rotated, right? Upon rotation, what has happened is the point on this side and point on this side, which were just opposite each other, they have now displaced, and therefore there is a twist that has occurred. Okay. Now, this twist as such, supposing I make a twist which is, let's say, some rotation over here. For example, if I take this circle, let me take this point and look at what has happened. Initially, it was like this. Later on, it has gone to this position. Okay, I'm talking about this point. It has gone to this position. So there is an angle that it has rotated by, right? Now let's call this angle as let's call this angle as, give me some name.
Alpha.
Some alpha. Okay. All right. Now, if I take this and if I take this, can I call this as angle of twist? Can I call this as angle of twist?
Yes.
Okay. So that's where the confusion is. Okay. So I'm going to repeat it once more. If I take a long rod like this and I twist it, okay, by an extent which is alpha, right? The amount of twist that has occurred is alpha. All right. If I take half of it and I twist it by alpha, same as this, the angle of twist is alpha. So far, okay? Whether I take the long one or the short one, if the circle is rotated by alpha, then angle of rotation is theta. So Let me call this as angle of rotation. Okay. So angle of twist and angle of rotation are the same, but I'll come back to that later. Okay. Now, what were straight lines over here have now become slant lines here, and this angle is the same as this angle, which means we are looking at shear strain as the angle that is formed over here. So far, so good. Is this clear to you? One is angle of rotation of a cross section that I've taken compared to a reference over here, and let's say that is alpha. I'm going to call that as angle of rotation. Aditya, can you mute the other people? This I'll also call as angle of twist compared to what I call this. This is gamma because I'm able to identify that from the grid that the slant that has occurred is to do with uh, what happens to the shearing that happens, and therefore this is a shear strain, that gamma, that I find out. Today there's absolutely no flow for me. So anyway, I'm trying my best. So far so good. Is this clear? Yeah. Now angle of twist depends on the total length. Supposing I take this and do this, the angle of twist that I take, let me put it like this. Supposing compared to this point, I have rotated this by alpha, right? And that's the angle of twist. And if I take only half of it and rotate it by the same alpha, what I will notice is this angle will not be the same for half as well as twice. I'm completely gone. Let me repeat it once more. Okay. Let's say this length is L. Okay. And it has rotated. This angle that it has rotated is alpha. Okay. Supposing I take half of it, I cut it in half and take only half of it, and look at what happens to this twist. The twist there will be lesser. This is not alpha. This is not equal to, I'm sorry, this is not equal to alpha, right? Do you agree with me? For example, if I take a very small piece over here and I want to find out what is the twist that has occurred over this small piece, the angle of twist there depends on this amount of movement that has occurred of the circle, right? So far, is that understood now? So I identified there are two angles that I'm looking at. One is an angle of rotation or angle of twist. The other is an angle that is due to the straining that has occurred, right? All right. Now, what I'm interested is in this, okay? But that is dependent on the angle of rotation that occurs on the circle, right? So now I can use geometry and connect these two, right? if it is gamma, which is the uh, shear strain times the length L, I will get R times alpha, correct? Angle with respect to a stationary point is the same with respect to the central axis of the rod. Sriraj, I'm not able to understand what you said. Angle with respect to stationary point is the same with respect to the central axis. I'm not able to understand, Sriraj, but do you understand this part? That if I take one circle here and one circle. See, I'm not able to see this on the camera. That's the problem I'm facing. I'm going to hold it for some time. Probably it will adjust. No, yeah. Okay. Are you able to get this? That the amount of shift that has occurred, if I look at it from gamma, it is gamma times L. Whereas if I look at it from the rotation, it is R times alpha, right? Or in other words, gamma is equal to R times alpha by L. Just purely from geometry, right? Like you, I'm also missing the class because I'm not able to get the response, so flow is not occurring. All right. Now, what am I looking at? I'm able to find out that there is a shear strain that has occurred because of this deformation, which is a twisting deformation. I also find that there is no change. There is no change in any of these, as if every cross section here, every ring over here is like a rigid body rotating. Are you with me? Right? If I take rings like this, every ring here is just rotating as a rigid body without any deformation that occurs in the cross section. So if I take any point in the cross section, it has only rotated, but it has not deformed in any way. It has not expanded or contracted. Are you with me, Aniket?
Yes, sir.
Okay. If that is so, the only strain that I look at is this shear strain, and all other strains are zero. Remember, this gap also has not changed. Apart from that, whatever ring that was initially present is exactly the same size as the other. The shape has not changed. The size has not changed. Okay. The only thing that I see is the rotation that happens, and therefore it is only the shear strain. Okay. So let's say this is the x direction that I'm looking at. Okay. Let me pinpoint y direction on this like this. This is y direction, and z is along the radius. Okay. So z is along the radius like this. Okay. I need to figure out what gamma is this. Is this gamma xy, gamma yz, or gamma xz? Which one is this? Which one is this? That's the question that I have to answer now. Okay. I already know from whatever it is, there is no change in the ring deformation that is occurring. The ring is oriented on the xy. What axis is the ring oriented in? What is the axis? What is the face that you see when I cut? It is the x plane, correct? X plane, right? So if I see the strain on the x plane, what kind of strains will I see? What I'm asking is, let us say this is x-axis, this is y-axis, this is z-axis. I'm now having a ring like this, whose face is directed along the x-axis, right? And I see that it has not changed in its shape or size, which means there is no strain occurring in that plane. What plane am I looking at? A plane whose normal is in the x direction, right? what happens to me is there is no response absolutely. I don't trust the response will be there. So Aditya and Dharmi, can you respond? Is that okay? I'm not getting the flow
Sure,
because
sir.
of that reason. All right.
Okay, sir.
Okay.
Okay, sir.
So the question that I'm asking, so you can answer me so that the class understands. If this is rotating only as a rigid body, I know that there is no strain occurring in that plane. What strains am I looking at? What strains am I looking at? I have epsilon x, epsilon y, epsilon z, gamma xy, gamma yz, gamma zx. If I can identify the strains that occur on the plane whose normal is in the x direction, then I can tell that all the strains on that plane are equal to 0. You understood now?
Yes, sir.
Now, can you tell me what strains they are that I have to now say they're equal to 0? On the plane whose normal is in the x direction.
Epsilon x will be 0.
Come again? Epsilon?
X will be 0 and y and z will be 0. As normal is
What plane is this? If it is x, that
YZ
is
plane,
normal to
sir.
it, y z,
yes,
right?
sir.
So I should have epsilon y to be 0, epsilon
Z.
z to be
Z to
0.
be-
Yes, sir.
So this to be 0, this to be 0. What else to be 0?
Gamma YZ.
Gamma yz is equal to 0. So far, okay? Is this clear? Right? We have only these two that appear. Okay? Gamma xy and gamma xz. Both have x as common. Okay? There's only a possibility of gamma xz or gamma xy. Okay? We have now zeroed down to just, and we also have epsilon x that we have to figure out. But what we found is that this length, this individual length, which is delta x, remains to be like delta x, which means there is no elongation that has occurred in the x direction. So this also goes to 0. All right. This also goes to 0. This implies that I may have only x gamma xy or gamma xz. Okay. So I'm going to draw this grid. This grid, this is the y direction, this is the x direction, and that which is coming out is the z direction. Okay. That's the grid that I looked at. Okay. And this deformed like this, right? It deformed like this. Okay. Now we'll ask that question. What gamma is this? Is it gamma xy or gamma xz? Once we are able to identify, it becomes easy. What is it? Which one is it?
Gamma xy.
Gamma xy automatically, because it is x is the direction that I'm looking at as the line element. So this is the x line element. This is the x line element. And this x line element is actually displacing in the y direction. And therefore, this is non-zero. Whereas if I take on the top face, then what will happen is I will have z coming into picture instead of y. Is this clear? So in this case, since I'm taking Cartesian coordinates, we have this difficulty. But if I take the polar coordinates, then whatever is in this direction is the one that we are talking about as a non-zero gamma. Okay. So there is only one shear strain that is present because of the torque that is applied to a thin tube. So far, okay? Yeah. Some response so that it's easier for me to continue because
Yes,
it's
sir.
getting to be too monotonous for me.
Yes, sir. Clear.
Yes, sir.
No, okay. Now we'll go back to what we asked. We have to relate between this and gamma. So now I can write this to be gamma xy. Okay. Another way to do that is I know this direction is r, this direction is theta, and the other direction is x. Correct? So I can also write this to be what instead of this?
So, shear
Alpha.
strain.
Instead of gamma xy, I can also write this to be what line element am I taking? What line element am I taking in the polar coordinate?
Theta.
X.
Theta, theta, correct? All right.
X.
Yx. Yx.
So because the face is perpendicular to the x direction.
The face is perpendicular to the x direction.
Or normal to the faces along x.
So what you're saying is theta x is non-zero.
No, the like x theta, like face perpendicular to x along theta direction, the strain is coming up.
But this is also equal to gamma x theta, correct?
Ah, yeah. Yes.
So we'll figure out why we found out this one, but we have not looked at this. We will look at it pretty soon. And let's say this is called gamma. Okay. Now it's
Yes.
pretty simple. Gamma times L, the total length, is the movement that occurs over here, which is also equal to R times alpha. Okay. Where alpha is the rotation of the end. Okay. We can also call this as angle of twist. Okay. Angle of twist. And this is the shear strain. Okay. So we started with looking at a tube. We twisted it and tried to find out what strains appear. We figured that all these normal strains are zero. Gamma yz is also equal to zero. Gamma xy or gamma xz may be present depending on which surface that I'm taking. To make it more clear, if I take theta as the direction, and then it is gamma theta x or gamma x theta, which should be present, and all the other strains should be zero, right? So it's a very simple case of one single strain appearing because of twisting. Okay, this I can also write this to be R times alpha by L. Okay, I'm going to do one more step over here. If I take the length to be L, then I get it to be alpha by L. But if I take it to be just delta x, where delta x tends to 0, what will I get this to be equal to? If I take a very small length and observe the twist, what will I get to be? L will become dx,
D.
right? L will become dx. For that small size, that the amount of twist will be very small, right? So what I'm looking at is d alpha by dx, right? So one relationship that I got is gamma is equal to R times d alpha by dx. This is the only information that I got from doing this entire exercise. So far, okay? So far, okay?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Sir,
Now-
what would be alpha by dx?
No, see, if I take this length, then it is alpha. If I keep on decreasing it, the total angle that it goes through for the same gamma, because this angle should not change. This angle should not change. So as I make it smaller and smaller, get over here, the shift here that has happened is very small, right? It depends on where I cut. It
Yes,
depends
sir.
on the length, and therefore it is d alpha by dx. Okay, because the rotation, as I make it smaller and smaller for the same gamma, is smaller, and therefore it is d alpha by dx. Okay, so this is rate of angle of twist. Okay. Okay. What's happening? Okay. All right. I have found out gamma. What can I use it for? What can I use it for? I found out gamma. From all this exercise, I could find out gamma. Based on the amount of twist, I'm able to now find this out. But what should I find out from all this? Okay, I got this information. So what? So what? How does it matter?
Strain.
What is it?
Strain.
Yeah, I found out the strain. Okay. I found out the relationship between strain and angle of twist. That's all I did. How is it useful?
You can find shear stress, sir.
I can find shear stress through what? Go ahead, go ahead. I have shear strain. You're right. Go ahead. Who said that? Your name, your name.
Bindu sir.
Can't hear you.
Bindu sir.
Okay. So, Bindu, you said I can relate gamma and the shear stress, correct? What's the relationship? What's the relationship between them?
E times tau.
Is it E times? Go back to what we discussed earlier. Just a couple of classes. We related shear stress to shear strain through
Poisson's ratio.
Poisson's ratio and elastic modulus. And I used a symbol for that. We also called it as rigidity modulus or shear modulus. Do you remember? G.
G.
Yes, sir.
Oh, yeah.
Do you remember this? Tau is
Yes,
equal to G times gamma, right? And therefore, I'm now able to find out the stress. So what I'm basically stating is, and what stress is this? If this is theta x, what tau is this? If this is theta x, this should be
X.
tau. Tau, quickly.
Theta x.
Theta x, right? Is also equal to tau x theta, right? So far, okay? So far, okay? Let's draw this stress and understand it. Okay? What is tau x theta? What does this x here mean? In tau x theta, what does this x mean?
The face perpendicular to x.
And what is that face?
Circular face.
It's this cross section, correct?
Cross section.
This is the cross section. So I'm drawing the cross section. Okay. whose normal is in the x direction, and tau x theta is directed along the theta direction, correct? Like this. Let's say the thickness is t, the radius is r, right? That's how I got this r here, right? And this is tau. Okay, tau x theta. Let's not worry about tau theta x for now. We'll come to it in the next class. This is what I figure out. Okay. What do I need to do? I need to find out if I apply a torque, how much of angle of twist will occur in that rod. So if I take this rod, and I apply a particular known torque, I want to find out how much of twist has occurred in this, right? How much of twist has occurred in this, or in other words, I want to figure out this alpha. Okay. Perhaps I also want to figure out what would be the shear strain due to this torque, right? That's the exercise I want to do, right? Now, if that is the case, but I have only shear stress acting on this, how will I find out the total torque that is applied?
The area which is multiplied.
Can you repeat it once more?
We should multiply it with the area.
If I multiply with the area, I'll get force, correct?
Yes, sir.
Okay, what do I do with that force?
So
What I have applied is torque.
Diameter.
Radial
be-
distance you have to multiply.
See, when I apply torque, what happens internally? When I apply a torque, what is the internal force that occurs because of torque?
Is
Shear
developed.
stress.
Is developed.
Twisting moment.
Twisting moment. So supposing I have to now relate to twisting moment, how will I relate to twisting moment? That's the question, right? Let's say T. T is equal to, how will I find out from this? I know the stress, I know the thickness, I know the radius. How will I find out the twisting moment out of this? Others can answer on chat also.
So tau x theta multiplied by area.
Tau, I'm going to just call it as tau now, okay? Because there is only one of them. Tau times,
Area, that is 2
what is
pi
the
r,
area?
2 pi
2
r
pi
times
r, 2 pi
T.
r times T is the area. Okay. Okay.
Into
and
the
then
diameter.
multiplied by r.
Multiplied by R will give me the torque. Is this okay? Is this clear? Now I have a tau here, but tau is given by G times gamma X. So let's substitute and see what I get. So I can now write this to be, this is 2 pi r square. So tau, I'm going to substitute for tau. So I'm going to put all those aside. So 2 pi r square T times tau, which is G times gamma, this is equal to 2 pi r square T times G times, now I can write this, right, which is R times d alpha by dx. So far, okay? Questions? Is this clear?
Yes, sir.
All right. So I'm going to erase this because I've inserted that over here. Okay. This is 2 pi r cube T times G times d alpha by dx. This is what I get. Okay. Intermediate results can be found out by looking at this. For example, if I just want to find out what would be the stress, I can easily find the stress to be equal to T by 2 pi r square t, 2 pi r square t, correct? Yes or no?
Yes, sir.
Right? And gamma can be found out by dividing by g. I have one question for you here. Are you able to recognize this term? 2 pi r cube t. What does area times the area times r give you?
The volume, sir.
2 pi r t is the area, right? The thin area. And I multiply by r. What should I get?
The moment of it.
Moment of inertia, J. This is the area times, how do I find out moment of inertia?
Times r or perpendicular line.
Times what? Can't hear you.
Sir, it's the radius.
Yeah. Times what?
Distance from
Lever
axis.
arm, sir, the perpendicular line.
Tell me what I should write here, yeah?
R, sir.
The times r, is it? Moment of inertia. What's the formula for moment of inertia?
So
If I have
mass,
one,
Rho times mass into I.
area moment of inertia. Moment of inertia, yeah? Area times,
Distance squared, sir.
what is the distance? If this is the axis that I'm looking at, what is the
R squared.
distance? And it has to be r square. You're taking a long time. This is A. Area times r square, right? Which is 2 pi r cube t, right? That's exactly what I get over here. And this is moment of inertia J, right? Now I can write this to be T is equal to TGJ times alpha d alpha by dx. I'm going to write this as alpha comma x. So far, so good. Is this clear? One last thing before I leave you. Sorry about a couple of more minutes. Let's look at this. I want to now rewrite this. I can rewrite this to be T by 2 pi r cube T divided by r, which means I can put an r over here. Clear? This is what? This is J, right? And therefore tau is equal to T r by J. So far, so good. Is this clear?
Yes, sir.
All right. And what is alpha comma x equal to? Let me not write it as alpha comma x. Alpha comma x is nothing but t by gj, right? So this is one formula I get. Now, if you look at it, I'm always using j over here directly, right? One last point that I want to make. If I have a length, just like what we did in axial deformation, if I have a length L, then this will become alpha by L, correct? So alpha by L from this equation is equal to T by Gj. Agreed? If you look at this equation, this is what I get. Or alpha is equal to TL by Gj. Okay? Where T is the force resultant, torque, or the twisting moment. L is the length, J is the geometric property, and G is the material property. But this looks very similar to what we did for axial, which is delta deformation, elongation is equal to play, right? If I take G, I mean E, if I remove E and replace by G, if I remove area and replace by J, keep length as constant and T over here, I will get alpha. Okay, so I don't have to remember this formula. I just have to replace appropriate quantities. I will get the angle of twist. Are you with me? I'm very sorry, I exceeded. We may have a class next, so let me stop here. So something that we have figured out today. Okay, tomorrow we'll make it concrete. Okay. Thank you. I'm sorry I exceeded time today.
Thank you.
Thank you.